So what I want to talk about today is related to the stuff we did last time about Euler circuits. Here is a typical example, something like this. And perhaps we remember from last time, does it have an Euler circuit or not? This means, can you use every edge exactly once without repeating any edges? And the answer in this case is no. There's no Euler circuit here, or Euler path, but let's just talk about circuits for now. There's no Euler circuit. Why not? It's because this has some odd degree vertices. That's the thing which you want to look for when you're talking about Euler circuits. So there's no Euler circuit here since there are some odd degree vertices. Like if I write in the degrees, these guys here are all 3. The other ones are even. The others are like 2 around the edge, and then there's a 4 in the middle. Ooh. But those guys on the side are all 3. Those being odd means there is no Euler circuit. Remember, the rule is there is an Euler circuit if and only if there's no odds at all. They're all even. So there are some odd degrees here, which means there's no Euler circuit. You can ask another question though, and if you're talking about these kinds of problems in real life, this is the natural follow-up question. It means since there's no Euler circuit, so if we want to cover all the edges, welcome. If we want to cover all the edges, that means we're going to have to repeat some, because this is what Euler circuit is all about, covering all the edges without repeating any. And I said it's not possible in this example, which means if you want to cover all the edges, we must repeat some. We must repeat some of them. All right, and the big question that I want to talk about today is, how many do you have to repeat in this example? So because there's no Euler circuit, it means you're going to have to repeat some. But for example, in this graph, could I do it only repeating one edge? Is that possible? Or do I have to repeat 2 edges or what? So the question for today is sort of our big question of the day. Not super big. I mean, we're going to be able to answer this question today. But anyway, that is how many edges must we duplicate in order to use every edge? That's the question. All right, because you're gonna have to repeat some of the edges, but how many? Can you do it repeating only one edge, or only 2 edges, or whatever? Actually, in this example, just because I know how to do this, you have to actually repeat 4 edges in order to make this one happen. But that's what we're going to talk about. It's how can you, and it's not actually because there are 4 odd vertices. But anyway, we're going to talk about sort of how can you look at the graph and figure out how many do we need to repeat. All right, so this one, maybe I'll just put that in parentheses. This one here requires 4 dupes. You have to actually go back across an edge at least 4 times in order to cover all the edges in that one. But this is our topic of the day. How do you know how many and which ones to duplicate? All right, let's look at, so we'll come back to that example. I want to look at an easier one. How about, this is just a smaller graph and a little easier to get a handle on. All right. There's a name for this, what I'm talking about here. I want to find the name for this is called minimum duplication circuit. So it uses all edges. and repeats as few edges as possible. All right, that's what I mean by minimum duplication circuit. You cover all the edges, doing as few duplicated edges as possible. All right, and there's a very basic idea here. The strategy. The idea is, first of all, I wrote idea. The idea. I grew up in the Boston area. This is how some people say idea. The idea is, first of all, find the odd degree vertices. So in this example, just look at all the degrees. That's a 2, that's a 3, a 2, and a 3. And focusing just on the odd ones, I don't care about the even ones. You find the odd degree vertices and then duplicate edges to make them even. So I'm going to do this maybe in another color here. I'm going to, so those 2 3s, I don't like them because they're odd. Ideally, if they're all even, that means we don't have to do any repetitions at all. But duplicate the edges to make them even. So what I mean by that is this edge going across the middle, I'm going to imagine that there were actually 2 edges there. And once I put that new edge, this 3 becomes a 4, and this 3 becomes a 4. All right? This is what I mean when I say duplicate edges to make them even. They used to be 3s, but when you add another edge in there, they now have become 4s. And now everything is even, and so I can draw an Euler circuit in the new graph. Right. And what does that look like? So that would be, I'll use my red line. That's like one of these. This is what we talked about last time. Maybe I'll go down to the bottom here, go across the middle, back across the blue version of the middle, and then back to the beginning. All right. So that is an Euler circuit in the new graph, which on the original graph corresponds to a circuit which duplicates that edge across the middle just once. All right. So this right here, the red one here, this is a, would you mind if I say MDC for minimum duplication circuit? With one duplicated edge. All right. We duplicated the one across the middle. Why did I repeat that one across the middle? Because that's the one which was connecting 2 of the odds, and if I made it, if I duplicated that one, it turns them both even. All right. This is the basic idea. We're going to do some more bigger examples, but that's basically how it goes. Any questions so far? Yeah.
Well, couldn't that graph, the original one, be a path?
Yes, yeah. In the original graph, there was an Euler path. That's right. But for now, at least, I'm just talking about circuits overall. Yeah. Yeah, we'll talk in a moment about the same thing, but for paths. It's called minimum duplication path, as you might imagine. All right. So can we just say a little bit more about this step in the middle here, duplicating edges? I would say my strategy here would be, when duplicating edges, try to pair up the odds and join them by doubling edges. So for example, let's look at just sort of like a bigger version. Sorry, I'm scrolling the words that I just wrote. A bigger version of the one that I was just doing. Let's try this one. So again, you begin by looking and finding the odds, right? And this is very much like the one that I just did. The odds would be like all these ones on the side. Those are degree 3 each. The ones on the corners are 2s, and the inside ones are all 4s. So those are evens, and I don't care about them. I only care about the odds. All right, and the words I said at the top. When duplicating edges, try to pair up the odds and join them by doubling edges. So I'm going to think of like these two at the top. They sort of go together, and I'm just going to insert a doubled edge between them like that. All right, that makes each of them 4s now. And so those guys are all sort of evened out. Ideally, we want them all to become even. And then I want to do a similar thing, on the others. And again, I'm going to pair them up in the most natural way, which would be I put one there, I put one there, and I put one there. All right, these are my 4 extra edges. So this one, when drawing the minimum duplication circuit, we'll use this time 4 dupes. 4 duplications are necessary in this example. Once you do those 4, they all turn up into evens. All right. Maybe could we just practice like what we were talking about last time? Maybe I'll have you guys. Can you draw in the minimum duplication circuit? That's like the red line. Let's start over here, and maybe go down first, and so on. See if you can draw the line in. You should be going across those blue ones twice, I guess. Or once for the blue one, once for the black one. Can you draw it in with 4 duplications? Talk to your friends if you like. Friends abandoned you. Are they really your friends?
I drew too small.
Yes, I agree with that. How's it going? Do you know where to do this?
Yeah, I'm just trying to figure out how to go back over the blue line.
You could, if you want, just go like here and then immediately come back. And then, do some more stuff. How's it going? You got one edge. I would suggest you could maybe go around this one and then come right back and then go do some more stuff. You don't have to think too much about these. You can pretty much make your line go where it wants to go. Can I give you an artistic comment? You should make, actually join those together. This makes it, it's like a small thing, it makes a big difference though, because otherwise it's hard for me to tell where it's meant to connect up.
Okay, yeah.
Good. How's it coming? It's good. You haven't messed it up yet, I don't think. That looks good. Everybody's looking good here. All right, I'm drawing mine. You guys all did things, I'm sure, a little bit differently from me, but that's fine. As long as you're not retracing any edges, except for those 4 edges which you decided you were going to retrace. So there's my minimum duplication circuit. It will use 4 duplications, and just for emphasis, they are right here, 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 and here, right? Those are the 4 duplications that I used. All right, I got another one for you. This is a little smaller. I'll let you do the whole thing. So first of all, it is up to you to decide which edges you're going to duplicate. Choose which edges to duplicate, and then see if you can draw in the circuit. This is 2 million duplications. Now this one. Yeah, that's the way. You went 3 times across the bottom. Yeah, that looks great. Still good here? All right, can we talk about this one? Looks like people are doing fine. You should, first of all, identify the odd vertices. There are the ones in the corners are all 3s. And then, remember my strategy was pair them up and connect them in pairs. So, and there are 2 ways you could do this. Maybe I'll take the top 2 as a pair together. So these 2 I connect up. Now they both became 4s. And then I'm also going to connect up the bottom 2. And now they both became 4s. You could have also done sort of like the 2 sides in pairs, but I decided to do the top and the bottom in pairs. And then draw in your line, and as usual, it can go wherever you want. And it can start and finish wherever you like, so maybe I'll start in the upper left, and I'll do a little something like this. I'm kind of making this up as I go. Something like that looks pretty good to me. All right. This is not exactly how any of you did it, but this is good enough. So how many duplications were there here? 2, right? There's this edge I used twice and this edge I used twice. 2 duplications are necessary in this picture. All right. Seems like everybody's doing fine with this. Let me just do one example. Sometimes it can be a little trickier. So remember the very first thing I did was I identified 4 different odds and then I joined them in pairs. The 2 on top and I joined the 2 on the bottom. I think actually most of you when you were doing it decided to do the 2 sides, and that's fine too. Sometimes actually that's not quite possible. So here is a bigger example. How about this? Oops. This looks kind of like a big sumo guy or something. All right. So, again, we begin by looking at this and finding the odd vertices, odd degree. Can we see any odds here?
The top, the middle box, not the middle.
You're pointing at something, surely
Those,
this,
yeah.
is that what you're talking about? Yeah, this right here is a degree 3. You're looking for 3-way intersections, or 5, I suppose, like anything odd. This one is a degree 3, and then there's sort of that similar one on the left side in the same position. Those are each degree 3s. I think everything else is a 4 or a 2. So those are the ones that we should focus on. And what's different about this example is you want to consider them in pairs. Now there's only 2 of them, so they naturally make a pair. But there isn't actually a single edge that connects them. So here, there isn't an edge from the 3 to the other 3. All right? And you might just say, well, can't I just sort of, when I add in my new edge, make it do that? The answer is no, you should not do that, because the whole point of what we're talking about is doing circuits which duplicate edges in the graph. So your new edge, you cannot just add an edge which didn't exist before. You can't add an edge which didn't You can't add an edge which doesn't already exist, because this whole thing is about duplicating existing edges, not about just creating new edges out of nowhere. Can't add an edge which doesn't already exist. So the strategy, what you do in this situation is you find a path connecting them and you duplicate every edge along that path. So we find a shortest path possible. A shortest path connecting them. And then duplicate all the edges along that path. All right, so in this example, my 2 odds, there is not a single edge that connects them, but there is a path going like straight across the top of 3 edges, and I need to duplicate each edge like that. So you join them up along a path, and you make duplications of each edge on the path. And let's just think about the degrees. So the 3 there, after I insert those blue ones, the 3, say, on the left becomes a 4, right? The other 3 also becomes a 4 because I created a new copy of that edge there. Unfortunately, this screws up the degrees of these other ones, right? They used to be 4. Now you see they are 6. So this is now, originally this one was a 4, and that's a 4. Now they have changed to a 6. But actually that's fine because 6 is still even, all right? And that's why this trick works. It does mess up the degrees of the other ones, but it causes them it messes them up by like adding 2, and so it stays even. If it was even before, it's still going to be even. All right. Duplicate all the edges along that path. So this example, in order to draw the minimum duplication circuit, we require, in this example, 3 duplications. All right. And maybe I'll draw in my circuit here real quick. I'll start in the upper left. Again, it doesn't matter where you start if you're drawing a Euler or minimum duplication circuit. Something like this. And I'll go around the chin, I guess. I'm just drawing the circuit real quick here. I hope you drew the picture kind of big if you want to draw this along with me. Like that. All right, that's a minimum duplication circuit with 3 edge duplications. It looks a little messy when I drew it. Now, so on our tests or whatever, and on the homeworks, sometimes I'm going to ask you just say which edges would you have to duplicate in order to do a minimum duplication circuit, and sometimes I might ask you just to also draw in the whole red line. You don't have to do it in red. I have a few examples. Let's not do the whole drawing of the circuit, but here is some more examples. In each case, just decide which edges need to be duplicated in a minimum duplication circuit. This is a lot easier than drawing out the entire thing. All right, there's 4 examples there. So you don't have to draw like the red line, but just decide which ones you would duplicate if you were going to draw it. And specifically, say how many duplications are necessary. ideas for this one? You want to kind of pair them up. So you take them, these two together, and then you have to kind of like I did here, find a path to the other end, each edge on that. You should be focused on the odds, right? And then the idea is just like here, pair them up. So take two of the odds and then duplicate all the edges of the path. So if you take these two, and then here, that's great. I don't think you want that one. So you've handled these two threes, but also those two threes. Mm-hmm. Yeah, this is great. Yeah, that's great. Maybe we could talk about these. Sorry, I had one more thing I wanted to get to before the end. I just wanted to leave enough time. People seem to be doing fine with these. The first one there on the left, you need 4 duplications. Actually, you can do it like I did in blue, or you could also pair them up kind of across the middle, like here, 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 here. That would work also. That's, again, 4 duplications. The one in the middle there, or this one here, you need only 1 duplication. 1 dupe. Here, this thing over here, you should start, you're always focusing on the odd vertices. They would be here, 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 and here. Those are all 3s, right? Those are all degree 3s. And you want to pair them up in a way where you want to sort of pair them in the nicest way possible. I would say you should maybe connect those and those. There you can do it with only 2 duplications. There are other ways you could try to pair them up, which might require more than 2, but you're looking for the minimum possible way. So this one needs 2 dupes. And then this one, this sort of like tuning fork type shape, this is actually sort of the worst one. If you look at the degrees here, that's a degree 1, which is odd. This is a 3, which is odd. That's a 2. Those 2s are even. These are 1s, which are odd. And then you have to join up the various odds. I can join the 1 and the 3 here just by duplicating this edge. But unfortunately, that leaves me with these 2 here, and in order to join up this one and this one, I have to duplicate all the edges around the bend here, which is unfortunate, but there's actually no better way to do it than you just have to duplicate everything in this example. This is kind of the worst case scenario. Here we have 5 duplications, and there's not any way to do it any better than that. You just have to go back across every single edge. All right. So, like I said, when this is on the homework or on the test, I might tell you only to do this much. Say which edges would you duplicate if you were going to. And then I might also tell you, this would be a harder question. I would say, okay, and then draw in the circuit, which covers everything with those duplications. All right. All right, one last thing to discuss, and this is not really difficult. I just wanted to say it at least once before I put it on the homework or whatever. Similar for paths. All right, what's the difference? So all of these ones we have been doing circuits, but what if instead you want a minimum duplication path? So I will say to make a minimum duplication path, which I will write MDP. Remember, the difference between like Euler circuit versus Euler path is an Euler path requires 2 odds and the rest even. So to make a minimum duplication path, this is what you have to do. You should, first of all, find all the odds, and then pair them up and duplicate edges so that all become even except 2, right? This is the only difference if you're trying to do a minimum duplication path. You, again, do the duplicated edges, which I've been drawing in blue. You do it so that all of them become even except 2. So you leave 2 odds, right? That's the only difference. Rather than trying to make them all even, you just keep 2 of the odds. Just keep them the way they are, all right? So let's try one big example. I'm not going to actually draw in the path, but we'll just decide which edges to duplicate. So this is a fairly rectilinear example, as they say. So a grid like this, and then I'm going to add in also some diagonals. One there, one there, one there. All right. So, and the question is, which edges should we duplicate to make a minimum duplication path? All right. Sometimes this is called an optimal parade route. This is like if you want to have a parade in your town that visits every street. You're probably going to have to repeat some of the streets in order to cover all of the streets. You might have to go back across some of them. Which ones should we repeat? That's the question. I'm waiting for everyone to copy the picture down. All right, anyway. What it is again, we're going to look for all the odd vertices. So we have to look through the whole graph and find which ones have odd degree. Those would be all of the 3-way intersections would be degree 3s. So that's a 3. I'm looking at all the 3-way intersections. Right? Those are all the 3-way intersections, I think, that I can see here. And the bottom right corner is a 3-way. All right? Those are all odds, and I think there's also a few degree 5s. Those are like where these extra diagonals go. This right here, it was a 4-way, but then there's an extra thing there, so that's 5. So this is a 5, this is a 5, this is a 5. I think those are all the odds that I have indicated. It's easy to miss a few, but I think I got all the odds circled. And now, we must duplicate edges as we do so that all of them become even, except I'm going to leave 2 odds like they are, all right? And you want to, just like in the other examples, ideally you want to pair up 2 odds and join them together to make them both even. And we're going to do this for all of them except for 2. Now, I'm going to decide ahead of time which of these that I'm just going to leave as an odd. I have to leave 2 of them as odds. And I think it doesn't really matter, although I look at this one, since this one is sort of isolated all by itself, I'm gonna leave this one like it is, because if I were to try to join it up with, say, that one, I'd have to duplicate 2 edges, which I don't like. I would rather just be duplicating 1 edge. So I'm gonna leave that one up top like it is, but the others I'm gonna try to pair up. And they're like, as usual, there are many ways that you could do this, but maybe I'll take those 2 on this side and pair them together. So now I fixed those. They're both even at this point. Maybe these 2 on the bottom I will pair up. Maybe these 2 here. I'll do these 2 like that, those 2 like that. How about that? I just added 5 edges, or I duplicated 5 edges. And now all of those ones which used to be odd are now even, except for the 2 at the top. All right, so now all are evens. Those 3s are now 4s, right? This, which used to be a 5, is now a 6. That's a 6. These are 4s. That's a 4. That's a 6. That's a 4. That's a 4. Right? Whatever they used to be, it's just been increased by 1. So now all are evens, except the 2 that I left alone. Except for the 2 odds. So our minimum duplication path will duplicate those edges, and there are 5 of them, right? So it will duplicate these 5 edges. So if this really is a parade in your town, if you and your kid friends, you should like try and sit on one of these streets, because it means the parade is going to go pass you twice, right? All right. And I think that'll do it. Thank you for your attention and presence. It means a lot to me to be here with you today.